Hi everyone, and welcome to Beginning Algebra. I am going to be streaming essentially a class I used to teach. Each class will be an hour long, and it'll cover all of the material that I have listed where you can see, wrong way, over on the URL. You can see there's a QR code and a URL there. I set up a Google Classroom where you can go and get all of the files that I've made for this class. So it looks something like what I have displayed here. So you can see it has like about this course and gives you like a little bit of information, and then it has all of the packets that I'll be covering. So today I should be doing probably packet 1, 2, and 3. I don't know if I'll get all the way through packet 3. But that's what I'll be covering. So if you want to, it doesn't want to scroll for some reason. If you want to follow along on this one or another one, you can actually go here and you can download the file and you can fill in the worksheet as I fill it in with you. So, yeah, like I said, this is just a live stream of a class I used to teach. I haven't taught it in a while and I kind of missed it. So instead of just making a YouTube video and having to go through all of the production quality of editing the video and stuff, I figured, well, maybe I'll just stream it and then I'll put that on YouTube and archive it in this Google Classroom so that I can have, an archive of it and look at it later if I want to. I don't know. But also, just in case anybody else wanted help with this topic, if it does well and it seems like people like it, I might do other courses like statistics or calculus or more advanced algebra. But I'm starting with the beginning algebra, okay? So by beginning algebra, I mean like pre-algebra. So some of the stuff we'll be doing, as you can see, is we'll start with like what types of numbers there are, different sets of numbers, and then doing arithmetic operations on whole numbers, which if you don't know what that is, I'll tell you in a little bit, and then integers, and then decimals. So one of the first things you learn in pre-algebra is how to work with negative numbers. So we're kind of leaning into that. Then we'll go into fraction stuff, and all of these first 5 packets are really just pre-work almost, making sure that you're ready to go into the algebra part, because a lot of algebra is dealing with fractions and negative numbers and stuff like that. So we're going to just cover that before we get into, having all the variables and everything and making it a little more complicated. So, yeah, and then we'll cover, we'll go up to solving equations, graphing, scientific notation, ratios and proportions, and then we'll just do some introduction to statistics. So I'm just going to keep streaming this every Wednesday until I get through all of it, and then we'll see what happens. Oh, about to have a cat classmate. So, okay, so I'm going to go ahead and get started. So, like I said, if you want to look for the files that I have, you can just go to the website and that's listed in the QR code there. There's also a short link for it. And you can get these files there. That's also where I'm going to put archives for the videos, so if you need to go back and look at it. Okay. So let's start with sets of numbers. So I want to talk about different types of numbers before I start talking about how to perform different operations on them. My cat is just, come on, walking all over my stuff. Okay, so a set. What is a set? A set is a collection of objects. It's the same thing as used when you're not talking about math stuff, right? Like a tea set is a collection of tea-related paraphernalia, right? So a set in math is a collection of objects, usually numbers, okay? Well, in the case that we're going to be talking about, it's numbers. Each object within that set is known as an element. So if you had a set of tea-related paraphernalia, your teacups would each be an element. When we're talking about math, we're going to have sets of numbers, and so each number is going to be an element. When you're talking about sets in math, you're going to use these symbols here, the curly braces, okay? These curly braces will go around the list of numbers. Oh no, my cat's about to jump on something very dangerous. She's trying to jump on top of my computer. Here, get down here. She just does not want my first stream to go well for me. It wants to knock over my computer. Okay, so those curly braces go around the set. So the set is, you list out all of the different, numbers and encapsulate them with these curly braces. Now, some of these sets are going to be really, really big, and you can't list out every single number in the set. And you would represent that using an ellipsis. That's what this is right here, the 3 dots. So the 3 dots are actually one thing, and that one thing is called an ellipsis. It represents, and so on. So if you have the curly braces, you'd say the set of, or the set containing, and then you could start listing out all the stuff. And if it's too long for you to write it all, you can put an ellipsis either in the middle or at the end somewhere. So I'll show you some examples of that when I explain the different types of numbers. So the first type of number I want to talk about are counting numbers. Excuse me. The counting numbers are the numbers that you use to count with. 1, 2, 3, 4, and so on. Notice here I've got an ellipsis at the end because I can't list them all, right? And then I've got the curly braces around saying, okay, here's all of them. And the ellipsis is inside the curly braces. Each number is also separated by a comma. Doing it like this is called listing notation. Whenever it has a pattern that you can distinguish by writing a few of them, you can list them out and then put the little dots. Now the other thing here is this weird double stroke N. If you were to write it, you can write it like this, or I usually do it like that or something. That is that letter you can use, instead of having to write all the numbers out, you can just write that N and everybody would know what you're talking about. They know that you're talking about the set of natural numbers. So the next one is the set of whole numbers. The set of whole numbers includes all those natural numbers plus the number 0. Now she's scratching my chair. Oh, it's the other cat. I got 3 cats, so there's probably going to be a lot of cat bombing in this. Is that a cat bombing? That's not a thing. But I have a little thing set up to where I can do a cat cam eventually. I just need to get it working, and they're all over the place, so I can't put a camera on them right now. Anyways, so the whole numbers are the natural numbers along with the number 0. So the way I remember when because a lot of people get the two mixed up, natural numbers, whole numbers. The way I remember is if you think of the 0 as a whole, like HOLE, the whole numbers contain the whole, okay? So it also has a weird double stroke extra, it's called blackboard bold, W, and that represents the whole numbers. Okay, so numbers can be graphed on a number line. At least all the numbers I'm going to talk about in this class. A graph of a number is the point on the line. So, and then that number itself is called the coordinate. So if I put a little dot, I say that is the graph of the number 3, and the coordinate of this dot is 3. Okay, so just to get used to the terminology here. So if I wanted to do the graph of the number 3, I just stick a little dot right there, and you want to put it right on the line. Don't put it above the line, don't put it below the line. A lot of people like to put it above the line for some reason. You got to put it right on the line, okay? So you can graph a single number, or you can graph a whole set of numbers. So if I want to graph the set A, which is the set of 0, 1, and 4, I just do 0, 1, and 4. Okay. Let me try doing it with my mouse. There we go. So why are we talking about graphs? It feels kind of weird. the reason I'm talking about graphs is the easiest way to describe the next set is through the use of a graph. Okay, so two numbers that are the same distance away from 0 on the number line are called opposites. Okay, so for example, the number 3 and the number -3 are the same number away from 0 on the number line, and therefore they are opposites of each other. So when you see a little negative number, it doesn't actually mean negative or whatever. It means the opposite of. That's what negative means. So when you see the -3, the negative means the opposite of 3. So that's important to remember when we start getting to all this stuff with like double negatives and everything, because then you're like the opposite of the opposite of, and it sounds silly right now when I say it, but when you start doing it, it is a little easier to think of it in that way, because it makes it easier to understand why it is you're doing these things that might feel a little weird. So the negative number, or the negative symbol, the minus symbol, represents the opposite of. So this set right here is one of the most important sets of numbers that you're going to deal with. Whole numbers, natural numbers, yeah, they're cool and all, but integers are where it's at, okay? Integers are used in so much stuff. If you ever start programming, you're going to use integers all the time, okay? So what integers are the set of whole numbers, so 0, 1, 2, 3, 4, and all of their opposites, okay? So it's 0, 1, 2, 3, forever and ever, and then -1, -2, -3, forever and ever in the opposite direction. So with that, you can see I have two ellipses, or ellipses, I think at this point when it's plural. I have one in the back and then one in the front. That represents it goes on and on forever in both directions. Now these are the numbers that when you write a number line that you label the number line out with. So an important thing to think about that is that if they're on the left of the number line, I think I either need to mirror my picture or start doing stuff the other way, because this is the left for me, but it's the right for y'all. So I need to mirror that next time. If you're on the left of the number line, you're a negative, and if you're on the right of the number line, you're positive. And then the number 0 is neither negative nor positive, because it's like right there in the middle. You can't be left or to the right of yourself. So if you want to find the opposite of something, you just do the other side of the number line. So the opposite of 8 would be -8. The opposite of -12 would be +12. And the opposite of 0 is not available. It doesn't exist. You could just say 0 if you wanted to be, no one's gonna yell at you if you say 0. I'm certainly not gonna yell at you. So the next few types of numbers are a little more difficult to describe, particularly the rational numbers. So the way we have to describe it is through the use of variables, and we're going to do a lot with variables in this class because it's a pre-algebra class, and algebra is when you start doing stuff without the variables. But there's no way to represent the rational numbers by like listing stuff out. The reason we were able to do it with the whole numbers, the natural numbers, and the integers was because there was a pattern to it. We can do like 0, 1, 2, 3, 4, and you just kind of can tell from looking at that the next number is 5, 6, and so forth. With the rational numbers, it doesn't work like that because it is the set of all numbers that can be written as a fraction. So that's a little weird, because if you do like 1/2, 0 and 1/2, okay, well, all that stuff in between that can be written as a fraction is also included. There's like not really a pattern for it. So the way you represent it is with what is known as set builder notation. So all the other ones we were using listing notation where we listed out the pattern, but with this one we have to do set builder notation. So the way you do that is you explain, like here's like the pattern. So it's all the set of numbers A and B, and then the line is such that. So the set of all numbers where a over b such that a and b are integers and b is not equal to 0. Essentially, all that's saying is all numbers that can be written as a fraction. So that really represents a whole bunch of stuff, okay? It represents most of the numbers that you are going to think of, like decimal numbers and things like that, okay? So if you can think of a decimal number or a fraction, it's going to exist in that. The next one, this one is, integers are super important. This one is probably the most important because this is all numbers that correspond to a point on the number line. So all those decimals, all those integers, everything. So you might be wondering, like, well, wait a minute. It feels like rational numbers already meet that. Well, they don't actually, because they only meet the ones that can be represented as a fraction. By the way, they're called rational because notice the root word here is ratio. Ratio means fraction, okay? So they're all the numbers that can be written as fractions, not because they, like, you know, have their mental health or whatever is in line, or not, that's not a good way to say it. Not because they're acting rationally or anything like that. It's just because they can act as a fraction, as a ratio. Real numbers are all of those numbers plus all the other stuff in there. Okay, so all that other stuff that can't be written as a fraction are known as the irrational numbers. Those are the numbers that cannot be written as a fraction. So it's a little hard to think about what those numbers are. The easiest way to think of them is they're the ones that when you put them in your calculator, you get a number that has a decimal, but there's no pattern to it. So if you see a decimal and it's like, it stops or it has a pattern, that's going to be a rational number. Okay, like if it's 0.3333333 forever, that's 1/3. 1 divided by 3. If it's 0.5, that's 1/2. But once you get stuff that has like a decimal with no pattern to it, you get to the irrational numbers. So a really popular version of that number, of irrational numbers, is pi. That's why it's so impressive for people to memorize it to multiple digits, because there's no pattern to it. You have to like just remember what it is. Irrational numbers, they don't even have a cool like way to represent them. It's just like real numbers that are not rational. It's like they're only defined by what they aren't. Okay. So the big thing with irrational numbers is they tend to be those things that are represented by a letter, like an Euler number, which is, you maybe seen an E before, or pi. Those are irrational numbers. Rational numbers are the ones that have a nice pattern, can be written as a fraction, and real number is just everything. Okay? Oh, the other thing about irrational numbers is they tend to happen because of a square root or some kind of root, some kind of radical. Okay? So you can think of it as the radical makes you irrational. Okay? I feel like there's a joke about a Roots Radical song or something in there, but I'm not clever enough to think of it at the moment. But so anyways, like I said, every number that's a real number can be put on a number line, even those irrational guys, okay, because they have some kind of representation on the line. So if I wanted to print these, to graph these out, I can just do it. 3 is not too hard. You just look for the 3 and you find it right there. 0 is also right smack in the middle. -5. 1/2 is halfway between 0 and 1, so it's right there. Oh, and I should be labeling these actually. So 3, negative, I don't need to label those, but I'll go ahead and label them. Anyways, 1/2, -2. Let me actually not label the ones that are integers here, because those are pretty obvious based on where they are. But these are going to be hard. All right, 1 1/3 means go up 1 and then 1/3. So it's going to be like right around there somewhere. 1 1/3. 2.5 is to 2 and then a half. 2.5. Negative 1/2 is over here. So go halfway to negative 1. 7/2. Okay, well, that is 7 goes, 2 goes into 7 3 times, so that's 3.5. So that's like over here. 7/2. And then square root of 14 or 17. So I know the square root of 16 is 4. Okay, so it's going to be just like a little bit more than that, right? So it's probably like around here somewhere. And if you weren't sure, you could stick it in your calculator and find out. Okay, so it's around there somewhere. I probably should use a thinner pen, but oh well. So let's look at these numbers in relation to each other real quick. So real numbers are just like everything. There is actually another set of numbers called the complex numbers. We're not going to talk about those here. You don't really start learning about those until like algebra 2-ish, and this is pre-algebra, okay? But there are other numbers that are not included, but for the most part, real numbers exist. Real numbers are all the numbers that you can think of, okay? So when it comes to real numbers, it includes almost everything except for those ones that I'm going to stop talking about. And between real numbers, you can either be an irrational number or a rational number, okay? And then if you're a rational number, you can be an integer or not an integer. Okay, so this is not really a set here. It's just a way to show how it breaks up. If you're an integer, you can either be a whole number or you don't get any other new cool classification. And if you're a whole number, you're either 0 or a natural number. So like the only difference between these two is that 0. Okay, so this diagram might be a little confusing because it has like some extra sections in there that you don't really need. But this one I like because it shows you how like they're broken down. So for example, real numbers is everything, and then it's cut in half between real and irrational. And irrational, they're just all by themselves. They don't have any new classification, okay? But the rational numbers can either be integers, whole numbers, or natural numbers. And notice, because the natural numbers are all the way in the center, if you're a natural number, then you're automatically a whole number, automatically an integer, and so forth. The same is true over here using this one. If you find it starts here, then it's also everything above it. Now let me delete that. Delete all this actually. I guess I can keep the C there. Okay. So let's look at some numbers and figure out what they are. So the trick is to figure out the lowest place it is on that list, and then it's everything above it. So the number 3. So the number 3 would be a natural number and then everybody above it, right? So it would be a natural number. It'd be a whole number. And then the one above that is an integer. That looked bad. Let me try that again. Can't draw these anymore. Okay. And then the one above that is the rational number. And then above that is the real numbers. So if you're an N, then you're automatically a W, a Z, a Q, and an R. Oh, I meant to mention, a lot of people are like, why the heck are rational numbers done with a Q instead of R? There's 2 reasons. One, real numbers are way more important, so they get the R. The other one is Q stands for quotient. Okay, so quotient is another word for fraction. Okay, so that's why they get the Q. Okay, so now let's look at number 2, which is the number 0. So 0 is not a natural number. Remember, natural numbers explicitly exclude 0. You don't get to include 0 until you get to whole numbers. Remember, they have the whole in them. So it's going to be a whole number. It's going to be an integer. It's going to be a rational number and a real number. I can't do Z's anymore for some reason. I don't know what happened to me. Okay. 1/2. Well, it's not even an integer, right? Because integers don't have fractions. They're just like the nice, fun numbers the nice, clean numbers that you can put on the number line. So it starts with the rational number. That's the ones that can be fractions, and then a real number. One of the things that I can be incredibly pedantic about are the differences between integers and whole numbers. A lot of people, they'll try to describe an integer, and they'll be like, oh, it's a whole number. It's like, actually, it's not a whole number. A whole number is is a subset of the integers. But anyways, so that's one of my things that I can be very pedantic about. But anyways, so -5. Okay, well, it's not a natural number because those are like counting numbers. They don't include the negatives. It's not a whole number because it also doesn't include negatives. The first ones to include negatives are the integers. So it's an integer, and then a rational number, and then a real number. Eee, that looks bad too. Square root of 17. That's one of those ones, if you stick it in your calculator, you're not going to get a nice, pretty number. You're not going to get a pattern. It's like 4.19 or something like that. So, but then like a whole bunch of other stuff. So this one cannot be written as a fraction. So it is an irrational number. And then it's also a real number. If you haven't noticed, all of these are going to be real numbers. So if you were given a test and you're asked, like, well, which type of number is this? List all the types of numbers that it is, or all the sets of numbers that it belongs to, and you can't remember any of them, just stick an R on all of them, because that's going to be the answer for almost all of them, except for the ones that have, like, these little I's in them, which, like I said, you won't see in this class. Okay, and then the next one, it's a fraction, so it's going to be one of the ones that can be represented as a quotient or the rational numbers. Now, that could have been a tricky one where, like, let's say it was 6/3. Let's say it was written like that. Well, 6/3 is actually 2. So it wouldn't have just started with quotient. It would have actually started down with the natural numbers. But okay, so now that we've talked about the different types of numbers, I can start talking about how to do arithmetic operations on all of them. So the next 2 packets are set up with how to do arithmetic on whole numbers, and then how to do arithmetic on integers. And you may be like, I know how to do this, and that's cool. Maybe you do know how to do it. That's fine. It's great, actually. The main reason I'm showing the stuff with the whole numbers, even though it doesn't really feel like algebra, is so you can look at it later and be like, oh, okay, it works the same with all these other numbers. Now I can kind of see the correlation. I'm not going to spend a lot of time doing it with whole numbers either. So, okay, let me scroll up actually. So let's do whole numbers, packet 2. Remember, the whole numbers are all the counting numbers, 1, 2, 3, 4, 5, and so on, along with the whole, the 0, okay? So these properties that I'm going to describe, I'm going to talk about them in terms of whole numbers, but they actually work for all real numbers. So these important properties are going to help us when we start doing algebra and all this stuff with x's and all that. Okay, so the first one is the commutative and associative property of real numbers. So I put real numbers there instead of whole numbers because it works with all of them. Okay, so you've probably noticed at some point that it didn't really matter in what order you added 2 numbers. So if you did like 5 plus 3, you get 8. And that's the exact same thing as 3 plus 5. You still get 8. Okay, so maybe you're one of those people who, if you're given a bunch of numbers, you start moving them around in your head, grouping them together. You can, or moving the order around in your head. That's totally fine. And the reason that's fine is the commutative property of real numbers. Okay, so commutative property of real numbers. So you can also do it with multiplication. Okay, multiplication says that you can multiply 2 numbers in whatever order. So that's the reason why 2 times 3 is the exact same thing as 3 times 2, because real numbers have the commutative property. So notice the root word of this is commute. You know, like back before the pandemic and we all had to drive, that drive to work, that was called the commute to work. Maybe you still have to drive to work, but the commute to work is your movement. Okay, so the commutative property is about moving the numbers. Okay, so it works for multiplication and it works for addition. Okay, subtraction and division are not commutative though. Okay, so 5 minus 3 is not the same thing as 3 minus 5. Okay, and 2 divided by 3, well, let me do a better one. 6 divided by 2 is not the same thing as 2 divided by 6. Okay, so subtraction and division are not commutative. You can't just switch them around. And that's going to be important later when we start doing this with algebra stuff. So if we wanted to use the commutative property to rewrite this, that would be, oh, I almost wrote 17. Okay, so 12 plus 5 is 17, yes, but if I'm trying to use the commutative property, that means I want to write it as 5 plus 12. Okay, 2 times 7, yes, is 14, but to use the commutative property means to rewrite it as 7 times 2, and that's totally cool. So you've probably also noticed that when you have a string of numbers, you can kind of like, not only can you switch the order of them, but you can kind of group them in whatever order you want. So for example, so in these examples, I'm going to use parentheses to say like, hey, do this thing first. Okay, so if I had 5 plus 3 plus 2, okay, so some people will say, well, 5 plus 3 is 8, plus 2 is 10. But other people will say, well, you know what? 3 plus 2 is 5, plus 5 is 10. Neither of them are better, or neither one is like the correct way. They're both completely fine. And the reason for that is the associative property of addition and multiplication. Okay, so I kind of buried the lead there. You can do it with multiplication too. I haven't shown you that one yet. But so remember, commutative means to move. Remember, if you're trying to remember the term, commute is to, move, like to commute to your job or to commute to school or whatever. Associative means to associate, like your associates. If you wanted to talk like, like a 1950s Rat Pack kind of guy, be like, yeah, these are my associates. Associate is the things that are grouped together. Okay, so to group them is kind of showing the order in which you do it. So you can do it with multiplication too. So 5 times 3 times 2. So if I wanted to be like 5 times 3 is 15, times 2 is 30. Or I could say 3 times 2 is 6, times 5, 30. Okay, doesn't matter, whichever way gets you to the answer more easily. Okay, so you can do it with multiplication and addition. So here it is written with letters. Essentially, just think of it as you're moving the parentheses around. You're associating two different numbers. So if I wanted to use the associative property to rewrite the statement, I would do 2 plus 3 plus 4. If I wanted to use the associative property of multiplication, I'd do that. Okay, so these are important to keep in mind when you're doing they're important to keep in mind when we start doing stuff with variables. Okay, all right, so the reason I want to talk about addition and subtraction with whole numbers is because I want to use these words, these terms that are important, and I feel like they're much less intimidating when they're done with words or with numbers that you're familiar with. So addends. Okay, if you want to add two numbers together, the two numbers are called addends. I always have to overemphasize these words because they're all a little hard for me to say for some reason. The addends are the two numbers that are being added together. And then the result, the answer, is the sum. Okay, so you'd say the sum of 5 and 3 is 8. Okay? So remember, subtraction is not commutative. So the order in which you do the thing is important. Therefore, the two numbers have different names because where they are in the problem is important. You know, first, second is different than like with adding. It doesn't matter who's first and who's second. You're going to get the same answer no matter what. But when it comes to subtraction, the first number is called the minuend, and the second number is called the subtrahend. Okay, minuend and subtrahend. Okay, and then the result is the difference. So the difference between 5 and 3 is 2. Okay, so remember, because the order in which you do them is important, they have different names, the minuend and subtrahend. Now, I actually hate saying those words. Like I said, I have to overemphasize them a lot. So you probably will never hear me say minuend and subtrahend again, but you will hear me say difference, and you will hear me say sum, okay? So, but these, they do show up, not those, these. They do show up, so I just wanted to bring them up in case you see them in something later. So, all right. So, like I said, I want to do these so that I can reference them later. So let's do some addition. So if I want to add 1270 and 456, let's just line them up. So 1270 plus 456, and we can use the calculator too. There's no shame in that. Got a 6, 7 plus 5. Okay, so sorry, if you don't know how to do addition in this way, you do it by columns. So you do the 0, you line them up in columns, then you do 0 plus 6 is 6, and then you do 7 plus 5 is 12, but you carry the 1 there. 4 plus 2 is 6, plus 1 is 7, and then you just bring that little 1 down, 1726. All right, if I want to do subtraction, 1507 minus 256, and remember, subtraction, the order is important. Okay, so if the bigger number was on the bottom, you wouldn't be able to just switch them. Okay, so 7 minus 6 is 1. 0 minus 5, I can't do that, so I'm going to make this a 4 and that a 10, and then 10 minus 5 is 5. Okay, then I do 4 minus 2, which is 2, and then I just drop down that 1 right there. Okay. So, another thing I want to point out is the phrasing of subtraction problems can be kind of confusing. Remember, the order in which you do them is super important. So sometimes you'll see these word problems, and they'll be like, find the difference between, or subtract B from A, and it's really important that you do it in the correct order, but the way that they word it might not be in the same order that you write the numbers. So whenever you see find the difference between A and B, so that always means do A first minus B. If you see subtract B from A, this part here is important, B from. So do it after, take it away from the other one, okay? So if you see B from A, that means do A minus B, okay? So if you see find the difference between 4 and 5, if you just see that phrase, find the difference between, that means just keep it in the order you see it. So that's equal to 1. If it says subtract 6 from 12, you start with the 12 and then you take the 6 from it. Okay? So the first time you learned about subtraction, you probably heard of it as like take away from. Okay? All right, let's move on. Rounding. We're going to do a lot of rounding in this class when we deal with decimals. A lot of what we're going to do is actually going to be using fractions though, so we won't have to do too much of it. But if you do rounding, to round, you look at the place value that you're being asked to round to, and then the number to the, is that the right for y'all? The number to the right of it, you look at it, and if it's 5 or higher, you round up, and if it's 4 or lower, you round down. So in this example, I want to round to the nearest 10. So this is the ones place, and then this one, this 6 right here, is in the tens place. Okay. So I know it's like 1, 4 something. The 1 and the 4, they're not going to get changed. Well, they could if 6 went up to like above 10. If 6 had been 9, it would have changed. But that 6, I need to figure out, does it go up or does it go down? Well, because 5 is right after it. 5 is bigger, so I'm going to round up. So you might wonder, like, well, why 5? Why not 6? A lot of people ask that. Like, why is 5 the number that rounds up? Well, if you think about it, that number can be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So because of that, 5 actually represents the other side. 0, 1, 2, 3, 4, 5. Okay, so this is the first half, 0 through 4, and then this is the other half. Okay, so let's round this to the nearest hundredth. So we got to get down 7 there. So it's 8. So the number after is 6. So I got to round up. So 8, 6, 3. Ready? Let's talk about inequality symbols. So the equality symbol, it's just the equal sign. But the inequality symbols, there's a few of those. There's a not equal to, there's the less than, there's the greater than, there's a less than or equal to, and then there's a greater than or equal to. Now, if you're like me, the first time you ever saw that, your teacher probably told you that, okay, like 1 is less than 2, and you want to think of this guy as like a little alligator who's going to eat the bigger number because he's got this huge appetite, right? Sure you guys saw that. We'll put an eyeball on there. Oh, it doesn't look good. Okay, I'm not going to waste my time making that better. Yes, I am. Okay. It looks worse every time I mess with it. Okay, I'm not going to mess with it anymore. So the little hungry alligator is going to eat the bigger one. When the math nerds who came up with this notation made this notation, they were not thinking of hungry alligators. I hate to break it to you. Okay, what they were actually thinking of is arrows. Now that we live in the world of typing, we actually use these things as arrows all the time. And that is what they were thinking of. So when you see the less than symbol, notice it's pointing to the left. Okay, it's an arrow to the left. So what that means, when you say A is less than B, that means A is to the left of B. If you see a greater than symbol, it doesn't mean the alligator wants to eat the B. Okay, it means B is to the right of A. Okay, now obviously you can think about it as a little alligator eating the bigger number. That's fine. Do what you want. But that's the real reason for it. So for example, 2 is less than 4 because 2 is to the right, I'm sorry, to the left of, it's to the left of, see when I draw the arrow? To the left of, it's the little less than symbol. 4 is to the right of 2. So notice it's got the little greater than symbol there. So that's like a fun thing to think of. And if you ever take an abstract algebra class and start learning about some cool stuff, you'll see these arrows go up and down eventually too, which is kind of cool. But that's way ahead of this. It's like if this is pre-algebra, then that's probably like 7 algebra classes from now. So who knows? Maybe I'll have a lecture series on those one day for you. Okay. Multiplying and dividing whole numbers. So I talked about terminology for addition and subtraction. Let's talk about some terminology for multiplication and division. And these terms, we're going to use a lot, okay? Particularly the one for multiplication. 2 numbers that are multiplied to each other are called factors, and the result is called the product, okay? So the product of 5 and 3 is 15. When it comes to, and I'll do that thing with the little box on it in a second. When it comes to division, remember, just like subtraction, because the order was important, each one had a different name, right? So when it comes to division, you have the dividend and the divisor. Okay, so the dividend is the first one, and then it's divided by the divisor, and then the result is the quotient. Remember I talked about quotients earlier when we were talking about rational numbers, and I was talking about the Q? It's all coming back around, okay? So when you write it in this this other notation, the longer form notation, the divisor is the first one, and then the dividend is the one underneath the house, okay? The dividend is the one that gets the little house. So I skipped this, but I want to talk about it now. There are some properties of multiplication that are important. Well, there is a property that is of multiplication that's important, and it's the fact that any number multiplied by 0 is always equal to 0. So b times 0 is 0. 0 times b is 0, because remember, multiplication is commutative, so it doesn't matter what order you do it in. It doesn't matter if 0 is at the beginning or at the end. It's always going to be 0. Now, division, because order is important, you got to think about it depending on where the 0 is. There's also some properties with the 1. You know, I probably should have put this too. B times 1 is equal to b, and 1 times b is equal to b. Yeah, I don't know why that's not there. I feel like it got disappeared somehow. So any number times 1 doesn't do anything to it. It's known as the identity element. If you're multiplied by 1, it doesn't change your identity. You stay the same, okay? So b times 1 is b. You know, that there, I feel like that was here and it disappeared somehow because of the that's why there's an a, because it was probably supposed to be a times 1. Okay, I'm gonna let it go. Let it go. So here we have division. The order is important in this case. A divided by a is equal to 1. So any number divided by itself is equal to 1. And then any number divided by 1 is still equal to itself. 0 divided by anything is 0. But you can't divide a number by 0. It's undefined. So there's a few different reasons for that. Some people want to say because it's how many parts there are. There's it's actually, the reason for it mostly is due to the fact that you can rewrite division as a multiplication, and I think we will talk about that later. So okay, so let's do some multiplication. Okay, let me get comfortable here. Okay, so 743 times 22. So 743 times 22. So when you do multiplication, you want to do by each digit on the bottom factor. Remember, in multiplication, they're both called factors. So I do 2 times 3, which is 6, then 2 times 4, which is 8, and 2 times 7, which is 14. So that's the first digit of the bottom factor. Now I need to do it for okay. Now I need to do it for the bottom, for the one in the tens place, the second 2. So it's going to just be the same thing, right? Because 2 times 3 is still 6, 2 times 4 is still 8, and 2 times 7 is still 14. And then you add the little things up. So 6, 8, and 6 is 13. 8 and 1 is 9, plus 4 is 13. So put that there. And then 6, and then 1. Okay. Oh, I feel like 8 and 6 is not. Ooh, I made a mistake. It is not 13. It is 14. I was just making sure y'all are paying attention, even though no one's watching this stream, so it doesn't really matter, right? Haha. Okay, so the next one is a huge number times 0. Now, that is a lot easier than it looks, because anything, regardless of how big that number is, times 0 is equal to 0. Now, dividing by 0 also has its own fun little special rules. You cannot divide by 0, so you would say undefined, or you can say UND, period. Okay. 0 you can divide by, so let me actually fix this. Where's my lasso? I need to make lasso a hotkey so that I can put this here. equal to 0. Let me use my smaller pen too. Okay, so equal to undefined. Oh, I guess that's not the smaller pen. This is... Oh, I thought I added the smaller pen to it. Okay, oh well. All right, 0 divided by anything? Always 0. So that one we can do. All right, let's try 30. Sorry, I'm gonna... I'm all perfectionist. So 1, 6, 3, 4, 6. Okay. Now let's go down here and do the last one. So remember the first one is the one that gets the house. Okay. So think of it as inheritance laws, right? For like old-timey inheritance laws. Oldest one is the one that gets the house, right? So in terms of division, the first one is the one that gets the house. So 3063. I'm sorry, 3036. Oh, scroll down for me there. Get my lasso. Move this down a little bit. Okay. And then 22. Poor 22. The second one that comes, so it doesn't get the house. Okay. So how many times does 22 go into 36? So what you do is you look at the number on the outside and you look at each digit and ask yourself, well, how many times does it go into that? So 22 will not go into 3 at all. 3 is way smaller. But 22 will go into 30. It'll go into 30 one time. Then you do 22 times 1 and you stick that down here. Then you do a subtraction. 30 minus 22 is 8. Okay, so how many times will 22 go into 8? It will not. Okay, so then we bring the 3 down. How many times will 22 go into 83? So 22 times 4 would be 88, right? So it's got to be less than that. So it's going to be 3, okay? Because 22 times 3 is 66. Okay, let me scroll down. So let's do a little carry in here. 7, carry that 1. 13 minus 6 is 7. And then 7 minus 6 is 1. 22 will not go into 17. But how many times, oops. How many times will it go into 6? And I already wrote the answer. I got too excited about writing that 8. 22 goes into 176 exactly 8 times, because 22 times 8 is 176. And once you get the 0 down here, this is when you're done. Okay. If you get a 0 there and you need to go, if you don't get a 0 there, you can go into decimals to keep going, or you can do like a remainder, a little r, stick it there. Okay, so I've got like 5 minutes left, but I don't really want to go to the next packet. So yeah, I wasn't sure if we'd get to integers. Ooh, getting too far ahead of me there. But next time, I'm either gonna do it on Wednesday or maybe earlier. I don't know. I'd like to try to finish the series sooner rather than later and do a different class. But at the latest, I'll do it on Wednesday. I will go over the packet 3. So remember, if you want to get all of this, if you want to get these packets and you want to see a recording of this video, you can go to the classroom that is listed over there. See the QR code with the little short link? You can get it there. I never had to use my, I want to show it to y'all though. I never got to use my calculator. Didn't need it. A little calculator. So yeah, I will do the next ones next time. If you came in and watched my stream, I really appreciate it. I'm just trying to archive all of my classes that I used to teach so that I can, I don't know, watch them when I feel reminiscent. Mostly, like I said, I miss teaching this class. I like it. It's fun. I teach mostly programming and game development now. So I wanted to do some algebra. So I'm going to do some algebra. So if you did log in and watch my stream, I appreciate it. Or if you're watching this video on YouTube, I appreciate that as well. All right, that's it. I'm gonna sign out.